So, in this lecture we are going to introduce the inverse function theorem. I guess this is the lecture 7th lecture 7, and today we are going to introduce the inverse function theorem. And this is actually a very important theorem in order to find the derivatives of invertible functions and to in fact find the derivative, I mean structuralize the derivative of the inverse of the function. Okay. The function need not be completely invertible, that is, it need not be invertible in its whole domain and codomain. We only require it to be locally invertible, that is, it is invertible in some open set, okay, in some open set around a point where it is initially differentiable, things of that sort. The other way to think of the inverse function theorem is a generalization of the fact that, so the generalization of the fact that if f is a function from R to R such that f is differentiable at let us say x naught, f prime x naught is non-zero, then or rather okay, so f from R to R is invertible, then we have that f inverse is differentiable, f inverse is differentiable at fx naught, right, and the derivative is given as, so the derivative of the inverse at the point fx naught is given as 1 upon f prime at x naught. Fine. Okay. Fine. This is something which we know, right? So now the thing which I was trying to say during the start of this lecture is that we do not require f prime to be invertible, right? So what do I mean by f prime to be not invertible? That is 1 upon f prime x naught. We do not require this to happen every time, but we can have some additional assumptions to it. Okay. Think of it like this way, that let me think of it in this way. Yeah, we can say this in this way, that suppose f is continuously differentiable. Okay, f is continuously differentiable, and suppose f prime of x naught is non-zero, but then this is basic real analysis, that then f prime of x0 must be strictly positive or strictly negative in some in some neighborhood of x naught. Okay, which implies that f is strictly increasing or strictly decreasing in some neighborhood of x naught. In that case, so we get a function, so we know that every strictly monotone function is injective, right? So what we get is that if I have a function which is continuously differentiable, so this actually follows from the continuity, that is why we require the derivative to be continuous, that if I have a continuously differentiable function such that the derivative at a point is non-zero, then obviously that at that point the derivative must either be strictly positive or strictly negative. But due to the continuity of f prime, that simply means that the derivative must be strictly positive or strictly negative in some neighborhood of x naught, and hence it must be either strictly increasing or strictly decreasing f must be strictly increasing or strictly decreasing in some neighborhood of some sufficiently small neighborhood of x naught. So that means it's injective in that neighborhood. So what we can do is that we can restrict down, we can sufficiently make this neighborhood small and small. We already have injectivity in our hand, so we can adjust the neighborhood in such a way that the function becomes surjective as well. In other words, it becomes injective. Okay. So in that case, the domain and the codomain can be made sufficiently close to x naught such that f is invertible in these neighborhoods. Fine. And this is what we call, so this is typically what we call local invertibility. Local invertibility. So what do we sort of conclude from here is that if I have a continuously differentiable function, then that such that it is differentiable at some point with a non-zero derivative, then that function is locally invertible. Okay, you can think of it as a fact as well. But you require f to be continuously differentiable. Okay, that is something which is required at this point. Okay, as an example, you can choose this map. Let's say f of x equals to x plus x square sine of 1 upon x4. Okay, so this is defined for all x non-zero and 0 if x equals to 0. You can check you can check that f is differentiable. F prime of 0 is 1, but you will see that if f is not increasing on any open set containing the origin. Okay, fine. This continuous differentiability is important to observe it. Okay. Rather, we don't require this at that point. I guess this would work. Whatever. So what we try to do is that we try to generalize it, as I said previously. Now, so our goal is to generalize this to functions from Rn to Rn. We keep it from Rn to Rn because after all we will require invertibility and linear transformation. Okay, I am talking about it once I talk about it here. Okay, so why do we require Rn to Rn? We will see it. Now, in this case, f prime at x naught, obviously if exists, is a linear transformation, right? It is a linear transformation, and it is a linear transformation from Rn to Rn itself, right? It is a linear transformation. Now, since it is a linear transformation, and in the one variable case, what did we require was that f prime of x naught was non-zero. Why? What was the main reason for it to be non-zero? For it to be non-zero was that we can take its inverse, right? And so here also we will require the same thing. We want to take the inverse of this derivative. It will come as the structure of the derivative while we study the inverse function theorem. But the invertibility of so here we are dealing with a linear transformation. We are not dealing with a scalar quantity, right? If it was a scalar quantity, then it would be sufficient for it to be just assuming it to be non-zero. That what ensures its invertibility. But here we are dealing with a linear transformation, right? And the invertibility of a linear transformation, it does not depend only on the fact that it must be non-zero, right? So now, okay, one more thing is that given a linear transformation between two finite dimensional spaces, this linear transformation is invertible, or one of the factors required for this function to be invertible is that the dimension of both the domain and the codomain is same. Okay, if the dimensions are different, then you cannot have a invertible linear transformation. Okay, now here, so as I said that here we require f prime of x naught to be invertible as a linear transformation, and the invertibility of a linear transformation, as I said, this does not depend only on it to be non-zero. There are multiple factors required for it. Okay, one of the one of the leading process to check the invertibility of a linear transformation is very simple. So let me just state it. See, we know that if T is a linear transformation from Rn to Rn, is a linear transformation, then this you can check on your own, that then if T inverse exists, then T inverse from Rn to Rn is also linear. Okay, this is pretty routine check. The checking of invertibility is actually quite easy. See, we are dealing with linear transformations over finite dimensional spaces, and therefore we can choose a basis and take a matrix of this linear transformation. Suppose the matrix of T is A. Okay, then T is invertible if and only if A is invertible, and we know that A is invertible if and only if the determinant of A is non-zero, and the matrix of its inverse is basically the inverse of the matrix. Okay, fine. Yeah, so to check whether a linear transformation is invertible, you can directly go to take any, so take the best basis, the standard basis, find its matrix, check whether the determinant is non-zero. If it's non-zero, then the matrix is invertible, hence the transformation itself is invertible. Okay, that's the best way to check. Fine. So as I said, that while generalizing, we do not only require that the derivative is non-zero, but as a linear transformation it needs to be invertible as a linear transformation, right? And the inverse of a linear transformation is also a linear transformation. Therefore, talking about the inverse of the derivative is sort of defined, because the inverse will also be a linear transformation. Now we state the inverse function theorem. In this lecture, we will not completely prove the inverse function theorem, but rather we will adjust the inverse function theorem in some sense that it becomes much easier to prove it, and the proof will be left for the next lecture. I would say this lecture is more important to understand the proof rather than the next lecture, because once we make these serious adjustments to the proof becomes very easy, right? It will become very easy once we make these adjustments. So adjustments are more important than the proof itself. Okay, there are multiple proofs to inverse function theorem. You can go and have a look at Rudin, the baby Rudin's book, mathematical analysis. I guess it's called mathematical analysis, I forgot the name. I guess it's called principles of mathematical analysis. Or you can go to Apostle as well, there is also a proof given, but I feel the proofs are quite complicated there. It requires a lot of rigorous manipulations of linear transformations and norms and so on and so forth. So these adjustments actually make it quite easy. Okay, let us state the inverse function theorem. So let E in Rn be open, fine, and let F be a map from E to Rn, which is continuously differentiable, that is its derivative exists and is continuous on E at every point in E. Suppose x naught belongs to E such that f prime x naught as a linear transformation from Rn to Rn is invertible. Then there exists an open set U in E, and or rather U in E, just not U in E, U in E containing x naught, and an open set V in Rn containing f of x naught, such that f restricted to U from U to V is a bijection. In particular, f inverse from V to U is differentiable at fx naught as it should be, and the derivative at fx naught is the inverse linear transformation of f prime x naught. Fine. Yeah, so this is the simple statement of the inverse function theorem. I shouldn't call it a simple statement, but once you go through it once more, it actually seems to be a bit simple. What does it basically tell you? So you start with an open set in Rn and you choose a continuously differentiable map on E. Then if the derivative at some point in E is invertible, what we have that it is locally invertible, f is locally invertible, that is I can have open sets in E which contains x naught and an open set V in Rn which contains f of x naught, such that f restricted from U to V is invertible and the inverse is also differentiable. It is differentiable at f of x naught, and this is given to be the structure of the derivative. Fine. Okay. So yeah, so let's make the adjustments first. Yeah, so I'm writing it we are writing it as a part of the proof itself. We will continue the proof from here itself in the next lecture. See, posteriori, that is once we have the inverse function theorem in hand, it's very easy to see that the derivative has the same structure as given in the theorem. Why is it so? See, we have I is equals to f prime of f, okay, where I is I from Rn to Rn is the identity map, Then, so f is differentiable at x naught, f prime is f inverse is differentiable at f of x naught. So then by the chain rule applied at x naught, what do we have? We have I prime at x naught is equals to f inverse prime at fx naught composed with f prime at x naught. Now the derivative of I is I itself, okay. You can try to prove it on your own. So now this is just I, so this is equals to f prime at fx naught, f prime at x naught, which implies that f inverse prime at fx naught, I mean the linear transformation is just f prime at x naught inverse, right? Yeah. So once we have the inverse function theorem in hand, the structure of the derivative is clear, okay. And we can easily see from here that the so that's a slight remark, that invertibility of the linear transformation f prime x naught is necessary, right? Otherwise this step would be not possible, okay. Fine. Now we make the adjustments. How do we make the adjustment? So observe that it suffices to prove the theorem for f of x naught to be 0. Why is it the case? In that case, in general, so if I try to prove it in general, choose the map f tilde x to be just f of x minus f of x naught, okay. In that case, you can observe that f tilde x naught will be 0, and so we can apply the inverse function theorem for f tilde x, and in that case the only thing which we need is the inverse of x in order to have the derivative, but that is also pretty clear. And if we choose y is equals to f of x, then observe that y minus fx naught, if I choose this to be f of x, then what do I have? So if I choose y to be f of x, then this implies that f inverse of y is equals to x, right? Yeah, okay. Then y minus fx naught is f tilde x naught. Fine. Yeah, so in that case f tilde inverse of, okay, let me not so yeah, this is f of x, right? F tilde x, then f tilde inverse of y minus fx naught will be equals to x, but x was f inverse of y, so that means we have that f inverse of y is equals to f tilde inverse of y minus fx naught. Yeah, so we have got the inverse of y, I mean the inverse function. Fine, so proving it for f tilde x will suffice, right? Yeah, so therefore we can assume that f of x naught is equal to 0. So this is the first adjustment we make. Fine, the next assumption, next observe that it suffices to choose x naught to be 0. Okay, then the general case would follow by choosing, we can just scale using this x naught, right? So I can just take f tilde x to be f of x plus x naught, so I can just scale it up, I can just simply scale it up. Okay, fine, right. Yeah, so in that case you can observe that f tilde at 0 will be f of x naught, and we already have so we have already chosen that f of x naught to be 0 in the previous assumption, chosen here f of x naught to be 0, so f tilde at 0 will be 0, and so we can again apply the same thing here. Okay, in this case we so by the way we structured the inverse there, we can do the same thing, that f inverse of y would be I guess f tilde inverse of y plus x naught. Yeah, this would be it. Okay, and then we can do the same, so like so assuming x naught to be 0 will also suffice. Okay, therefore it suffices to choose x naught to be 0 as well. Fine, so what we conclude, so yeah, therefore what we have is that f of 0 is 0 and f prime at 0 is invertible. Fine. The final assumption or the final simplification we make is the following, and this is a more rigorous sort of a simplification. We choose the derivative at the origin to be identity map. Okay, the identity transformation from Rn to Rn. Why is it so? Then in the general case we can choose f tilde to be the map from E to Rn such that f tilde of x equals to f prime at origin inverse times fx, and by choosing f prime at origin to be identity, this is an invertible linear transformation, so this is well defined, right? We can apply the special case to it. This is still a linear transformation, f tilde f prime at 0 inverse is still a linear transformation, and we also observe that f tilde at 0 is 0, and that if I take the derivative you can simply follow it from the so what do we require here is that I have the linear transformation here, so I will have it in this way, right? F tilde this inverse f prime at 0, this will just be identity, right? It will just be identity, so we can apply the special case of the inverse function theorem to here, to this f tilde, and we are good to go, right? Okay, so let me just explain it a bit. So therefore by our assumption, if I choose f prime at the origin to be identity, assumption applying the inverse function theorem, there exists open set u prime containing the origin, which is what we are working with, containing the origin, an open set V prime also containing origin, because we have chosen the f evaluated at the origin to be origin, open set V prime containing the origin, such that f tilde from u prime to v prime is a bijection, right? And f the inverse of f tilde from v prime to u prime is differentiable at the origin with derivative, which we have just seen, with derivative to be the identity. Now we have chosen f tilde in such a way that fx is nothing but f prime at the origin times f tilde x, right? Right. Now f tilde is a bijection. F prime at origin, which is the identity map, it is also a bijection. Therefore, f is a bijection. Therefore, f is a bijection from u to the image of v under f prime at origin, right? You can see that the f prime is, yeah, as I said, it's also a bijection, right? Now the important thing to observe here is that, see, u prime was open. I have missed here, this should be u prime. Now u prime was open, so I need to apply the inverse function theorem, or rather prove the inverse function theorem. So I need f prime at 0 applied to v prime is also open, but that's actually open. Why is it open? Because, see, the linear map f prime at 0, okay, it is continuous. We have chosen the map to be continuously differentiable, and it's, in fact, it's the identity map, so it's obviously continuous. Its inverse is also the identity map, that's also continuous. So that is something called a homeomorphism. So a map between two topological spaces which is continuous and the inverse is also continuous is a homeomorphism in some sense. So it's a homeomorphism, yeah, and hence, and under homeomorphism, the images of open sets are open as well. Like we know, in case of continuous maps, inverse images of open sets are open. In case of homeomorphisms, images of open sets are open, and hence, and v prime was already open, so f prime 0 applied to v prime is open as well. Fine. Therefore, consider we can finally consider the transformation, rather the map, sorry, not the transformation, the map f inverse from f prime of 0 applied to v prime to u prime. Now we had already had that fx is equals to f prime at the origin composed with f tilde x, right? Then this immediately implies that f inverse of to some y is f inverse of f prime at origin inverse y for all y in f prime at 0 v prime. You can check it on your own by just choosing f of x to be y and making adequate substitutions. Keep doing it. It's very easy to check it. Okay, just use the fact that f tilde is a bijection from u prime to v prime. Okay, in some sense, therefore, f inverse is differentiable at the origin. Fine. Yeah. Therefore, it suffices to choose the derivative to be the identity transformation. So what all we have? Let me just repeat once. So we choose f of 0 to be 0. We choose f prime at 0 to be invertible, and we choose that f prime at 0 to be identity, right? So these are the things which we will be using to prove the inverse function theorem, and the inverse function theorem will be efficiently proved in the next lecture. So meet you guys in the next lecture. So let's continue the proof of the inverse function theorem. Let us first recall the statement for for completeness. So the inverse function theorem basically says that if you have an open set E in Rn and f is a continuously differentiable function from E to Rn such that the derivative of f at x naught in E is invertible. Okay, then there exists an open set in E which contains x naught and a corresponding open set V in Rn which contains f of x naught, such that f from u to v is a bijection and the inverse is differentiable at f of x naught, and the derivative of the inverse is given, which is very analogous to the one dimensional chain rule. Okay, and in the previous lecture we had seen that we can prove this with some additional assumptions, that we can prove this by simply choosing x naught to be 0, f at x naught to be 0, that is f at 0 to be 0, and that the derivative at x naught to be simply identity. Okay, these were the assumptions which we made in the previous lecture, rather these were the reductions which we had made in the previous lecture, and we had also shown in the previous lecture that proving the inverse function theorem having these in hand will suffice, right. So now we continue the proof. Okay, so let gx be f of x minus x. Okay, then we can see that what do we have, then g of 0 is 0, fine, g prime at 0 is also 0. Now once g prime at 0 is 0, this immediately implies that the partial derivatives at each of the components at the origin is still 0, right. Now we are given that g is continuously differentiable, right. Now that is, all its partial derivatives exist and are continuous. Now since g is continuously differentiable, therefore there exists a ball. This follows from the definition of continuity in E, such that the norm of del g del xj at x is it is less than or equals to 1 over 2n square, and this happens for every x, right. Fine, this follows from continuity, and this limit has nothing special. We are just choosing a very good small enough number, nothing else. Now also we are given that f is differentiable at at or on E, right. F is differentiable on E, that is what is given to us. And moreover, recall that we had seen that if f is differentiable at some point, then the directional derivative at that point can be written as a linear combination in terms of the coordinates of that point and the partial derivatives of the function at the point, right. Yeah. So now for any x in B0R and some vector v, we have that the norm of the directional derivative at gx, this should be equals to summation j is equals to 1 to n. Why is it happening? Because the function f is given to be differentiable in E, right, and the ball is contained in E. That is why all these are taking place. So I have this follows from some previous lecture, if you recall, but then we can use the triangle inequality to write it in this way, summation j is equals to 1 to n. So this becomes mod of vj norm of del g over del xj at x. But we have seen that this norm is less than 2n square, and this modulus of vj, this should be less than equals to norm of v, right. If you recall that if v is an n tuple, then the absolute value of each tuple is less than or equals to the norm of the complete vector, right. So this is in fact less than or equals to summation j is equals to 1 to n norm of v times 1 over 2n square. But then none of these are dependent on j, right, as the index j. So this is nothing but 1 upon 2n square times n times norm of v. This is just 1 upon 2n norm of v. Fine. Therefore, for all xy in B0R, by the fundamental theorem of integral calculus, or the fundamental theorem of calculus. What do we have? We have gy minus gx. This can be done as integration 0 to 1 of the derivative of the function at this point, right, dt. The integration of a vector valued function is just taking the integration component wise, nothing else. Each of the components of a vector valued functions are real valued functions, right? Therefore, if you want to take the integration of a vector valued function, at least in this case, you can just think of taking it component wise. So it is just a real integration. So it can be written as 0 to 1. So this is just the directional derivative taken in the direction of y minus x of the function at this point dt. Fine. Now we know that the norm, the magnitude of the directional derivatives are always less than or equals to, in the direction of some vector v is always less than or equals to 1 upon 2n times norm of that vector, right? Therefore, this norm should be less than or equals to 1 upon 2n times norm of y minus x. Okay, right? Thus every component should also have the same upper limit, right? This implies that every component of this vector should also have the same bound. Fine. But then gy minus gx must also have the same bound. But this implies that gy minus gx has magnitude at most the same, right? Which implies that it's a contraction, which implies that g is a contraction, or rather a strict contraction. Fine. Now recall in the previous lecture when we had studied, in the previous lecture when we had studied the contraction mapping principle, there we had a corollary which I said that will be used in the inverse function theorem, and let us go back there. So I guess this was the statement. Yeah, so this was the statement that if I have a ball in Rn around the origin, and I have a function g such that g at 0 is 0 and g is a contraction for every xy in that ball, then if I choose the function f from the ball to Rn so that fx is defined to be x plus gx, then what do I have? I have f to be injective, and that the image of the ball contains the ball around origin of radius half of the initial radius, right? So we will essentially make use of this here. Okay, therefore, so I am just writing here by that lemma. I hope you recall, I didn't number that out, so I can't use it. So by that lemma, now f is nothing but g plus I. So this is injective on B0R, and the image of the ball contains the ball of radius r by 2, and then f inverse from B0R by 2 to B0R is defined on this ball, right? Clear? Okay. So we have made up with an inverse function. Okay. Now also, so let me phrase this statement to be 1. Now 1 using y equal to 0 implies norm of gx is less than equals to half times norm of x for all x in B0R, and which implies by triangle inequality that half norm of x, this is less than equals to norm of gx, but gx was basically, g was taken to be fx minus x, so this essentially becomes 3 by 2 norm of x. Fine. Okay. Yeah. So okay. So yeah. So we have this bound using the triangle inequality and the fact that the norm of g of x is less than equals to half norm of x. Now what we do is that so what we have is that we have an inverse function from the ball of radius r by 2 to the ball of radius r. So now what we do, so let u let v be this ball, because we need a bijection, right. So not yet we still have that f inverse, it contains the whole codomain, that is something she required, because the function is actually having its codomain in b0r, right. I mean f, the image of b0r under f. So what we do is simply is that we take u to be the intersection of f inverse v with b0r. So we are just restricting it to the codomain on which we can say that f is a bijection, right. So I can take a to be just f inverse v intersection b0r, fine, and hence f is a bijection here. Therefore f from u to v is a bijection. Clear? The bijection. Now v is open, right? Now v is open, so this implies f inverse v is open because f is continuous. This implies f inverse v intersection b0r, intersection of two open sets, is equal to u is open. Fine. Now basically if something is open relative to a ball around origin, it is basically open in Rn. Okay. Now so all we left to show is that f inverse is differentiable. Show that f inverse from v to u is differentiable at the origin with derivative I inverse equal to I. Fine. So in other words, what we need to show is that is limit x tends to 0, x is in v minus 0, in norm of f inverse x minus f inverse 0 minus I at x minus 0 divided by norm of x is equals to 0. Fine. This is what we need to show. Now f at 0 is 0, so f inverse at 0 is 0. Fine. Now f at 0 is 0, so this is something we have. Therefore, and f is a bijection, right, so it's injective here, right. So we have this, simply we have a simplification, nothing else. Fine. Now what we do is that we just use the sequential criteria of limits. By the sequential criteria of limits, what we can say that limit, this is equivalent to show, we show that limit n tends to infinity, norm of f inverse of xn minus xn upon norm of xn is equals to 0, where xn is basically a sequence in v minus 0 such that xn converges to 0. Fine. Fine. Now let yn be the sequence f inverse xn. Okay. Then by the structure of f, yn must be in b0r, xn must be f of yn, and furthermore we have from the inequality we had previous that this is less than equals to norm of xn and this is less than equals to 3 by 2 norm of y. Fine. Now xn goes to 0, right? Therefore yn should also go to 0. This is some sort of, you can think of it some sort of as directly as the squeeze theorem. Now since xn goes to 0, yn goes to 0. Fine. But as soon as yn goes to 0, therefore limit n tends to infinity, norm of yn minus f of yn upon norm of yn equals to 0. This is what we need to show. Therefore it suffices to show this. Okay, one more thing you can easily observe it from here, that the ratio of yn and xn is also bounded. Okay, is bounded, and the inverse is also bounded. I mean the ratio yn upon xn is also bounded. Norm of yn upon norm of xn is also bounded. Okay, once we have this, now we can write this as limit n tends to infinity. See, this part, this complete thing can be written with a slight adjustment to be of this form: f of yn minus f of 0, because f at 0 is 0, minus f prime at 0, it was to be identity of yn minus 0, right? And we know that f is differentiable at origin, therefore this is 0, which implies that limit n tends to infinity so this is 0, and that's the end of the proof. Fine. Okay, so let this lecture be up to this much. In the previous lecture we had talked about the fact that how to check whether f prime at x naught is invertible. Just consider it to be since it is a linear combination, you can since it is a linear transformation, you can choose the best basis provided for the vector space, which is obviously the standard order basis. Take the matrix, check invertibility of the matrix, and take the inverse of the matrix, and you will get the inverse transformation, as well as you will get to know whether it's invertible or not, right? So in this case you will have the matrix, or rather, since we are talking about since we are simply talking about, we do not need to get into the terms of basis as well here, since the linear transformation here is simply the derivatives. In an arbitrary linear transformation, this is the procedure you obviously follow, but here in this case we have simply the derivatives, and we know that the matrix associated to this derivative transformation is nothing but the Jacobian matrix, and constructing the Jacobian matrix directly seeing the function is quite easy. So just construct out the Jacobian matrix, check whether it's invertible or not, and that's enough, right? The process of checking its invertibility is same as for any arbitrary matrix, right? Yeah. So okay, so this is the end of this lecture. In the next lecture we will be starting following the notions of implicit function theorem. Okay, so meet you guys in the next lecture.